Ah, I'm back. Hey, how's it going? Day 3 calculus. We're going to be talking specifically about parallel, perpendicular, and some terminology again. You'll find that a lot of these first few days is spent talking about things like terminology, understanding the language in which the problems are asked in is sometimes the most difficult part of a math problem. If you don't understand how the math is approached, the language it's using to try to tell you what to do, then you will quickly find that the math becomes virtually impossible. This is because, in general, math and English are not the same language. They just aren't. I have said for years that especially as you get farther along, math should be considered a foreign language credit. This is because the terminology we will talk about, the symbols we will talk about, is another language. And you have to know it and understand it the same way you have to know the verbs and their conjugations in Spanish in order to speak fluently in it, or in French in order to speak fluently in it. The same way that you can combine them together in different ways, some of which are right and some of which don't make any sense, works in a foreign language the same way it does in math. Like there are some symbols that if you put them together in a math problem, people look at you and go, you just spoke weird. What are you doing? We don't understand. Because math is a language. It follows specific rules, and once you learn those rules and how they can fit together, it's easy to piece together what a problem is asking and how it's asking it. So let's take a look today at some terminology first, and then we'll deal with our last little subject for this week, which is going to be slopes and parallel and perpendicular. Should be fun. Again, a lot of this should be review for you, which is great. If you're struggling with any of this, our Zoom session is going to be today at noon. So feel free to come by and ask questions, or just say hi. It's up to you. All right, let's get started. First thing to note here, I've already started using some terminology that I should make sure to note. When I have equations, such as two lines, we're going to call them line number 1 and line number 2. You'll often see me use some shorthands to indicate a few things. For example, if I want to talk about line 1 could have an intercept. Call it B. But if I'm talking about line 1's intercept, I would call it B subscript 1 to differentiate it between the intercept of the second equation. Because I don't want to confuse, since they're both intercepts, and they're both intercepts of lines, I want to make sure to make it clear that this intercept comes from the first equation, and this intercept comes from the second equation. Similarly, if we want to talk about slopes, the slope of our first line we could call m sub 1. Because m is our definition for slope, 1 is which line it's talking about. It is the slope of line 1. Whereas if I ask the slope of line 2, we'd use m2. Now, it is far more common to use the subscript when it comes to points when you're talking about them for a problem. So like, for example, if you have the first point, we typically refer to as x sub 1 and y sub 1. Because each point will have an x value and a y value, but each of these x and y values are referred to by which point they're talking about. So this is the first x value. This is the first y value. Whereas the second point, we'd use x2 and y2. And note that these two go together because they're both from the second point. x1 and y1 go together because they're both from the first point. And so you can't mix and match. There's no way to get, x1, y2, because what is that? That's nothing. That's the x value from the first point and the y value of the second point. That isn't either one of these. It's nothing. And so you'll often see in mathematics using subscripts. Do you know what the subscript is? Just to differentiate which slope it is, or which intercept it is, or which line it is. It is even common in mathematics to use things like L1 to talk about line 1, and L2 to talk about line 2. And if you remember your geometry, you might remember P1 and P2. Although in geometry it's a lot more common to use things like different letters. But in calculus, they're all points, so why would we call them by a different letter? That just gets confusing. Just be like, this is the first point, this is the second point. That's why it's P1 and P2. So let's talk about parallel perpendicular. Parallel and perpendicular are both properties. Parallel and perpendicular are comparisons of how these lines interact in space. So again, we're talking about a property which is either true or false. It's the only possibilities. And these are exemptive properties, meaning if you know it parallel is true, then that means that perpendicular has to be false. If you know perpendicular is true, that means parallel has to be false. However, there is a third option, neither. Each one of these follows that dichotomy, meaning if parallel is true, then it's not perpendicular and it's not neither. If perpendicular is true, then it's not parallel and it's not neither. If neither is true, then it's not perpendicular and it's not parallel. And so for each one of these, the definition of parallel, perpendicular, and neither dictates the definitions of the other two, whether they are true or false. Now, the definition of parallel means that there is the same or equal distance between two lines. Now, in this case, the word distance is a more standard term of distance. We typically like to think of distance between 2 points, like here's point 1, here's point 2. And so we talk about the distance between those. When we talk about lines, there's what's referred to as distance is actually the minimum distance to make sure it's always the same number. Perpendicular means that these lines intersect at a right angle. This means that you have an angular definition as well. But you can also talk about parallel by a similar definition. And so there's multiple ways to talk about this. And so perpendicular has an intersection point. That's a big detail. And it happens at a right angle. Parallel has no intersection point. Which is a detail that's very important. Parallels never cross. Perpendiculars cross with a specific property. Now neither intersect, but not at a right angle. Let's put these in terms of a picture. So I'm kind of just drawing a couple random lines here. Beautiful. And let's go with this one. So when you have a more complicated picture, you have to pay special attention to what's going on. So let's talk about this. So when you talk about this, you have to talk about two lines at a time and say what relationship they have. So for example, I could say something like red and blue are perpendicular. Perpendicular. I can't spell today. They are perpendicular. How do I know that? Well, they intersect at a right angle. And I can verify that using a process we'll talk about in a moment. But if I talk about red and orange, these are neither. Because while they do intersect in one place, right here, that intersection point is not a right angle. I can see that using the grid lines. Similarly, I could talk about blue and orange. And they are also neither. Because again, blue and orange do intersect here, but where they intersect is not actually at a right angle. I can again use the lines we are given. Now let's look at one more line. Let's say purple. So we can see in this picture that purple and blue would be parallel. They do not intersect, and you can see how it maintains the same distance in between them all the way along our paper. It never gets thinner on one end, indicating that they might intersect farther away, like down here somewhere. It stays consistently like railroad tracks. Okay? In the same vein, these statements can be reevaluated using the purple one. So we could ask questions about what happens with purple and red. We could ask questions about what happens with purple and orange. And you always have to do this in pairs. When you talk about parallel, perpendicular, neither, you are always investigating a pair. This is always the case. Because I can't talk about parallel with only one thing. I can't talk about perpendicular with only one thing. It doesn't make any sense. Now, as you can imagine, because of how these are interacting, something has to be happening with their slopes. And if you remember the properties, there is a very unique test to determine parallel, perpendicular, neither that specifically involves slope. Let's talk about those two things. Parallel. The test for parallel is that the two slopes have to be equal. So remember, we're using a terminology here. This is the slope from the first line you select. This is the slope from the second line you select. And they must be equal to each other. To be perpendicular, there's a couple ways to do it. First way, this is the way I was always taught. You multiply the slopes. If they multiply and become -1, it means they're perpendicular. And so these are your tests. This equality is not guaranteed. You have to test it. And so you have to find the slope of the first one, you have to find the slope of the second one by any means necessary, and then perform the test. Are the two slopes equal? Yes or no? If the answer is yes, then we say they're parallel. If the answer is no, then that means it is one of the other two. Okay? So again, it's a test. You have to check to see if they are going to be parallel by investigating their slopes. You have to check to see if they're perpendicular by investigating their slopes. There is an alternative version of this. These are called, I believe they're multiplicative inverses. I'd have to verify terminology. I haven't taught Algebra 1 in a long time. What this means is that if I plug in M1 and M2, do I verify if this is true? That's what matters. Is the equality of this statement true? Because if it's not true, then we say it is not perpendicular. And then how do we check neither? Neither just means parallel and perpendicular both fail. They have to both fail in order to determine that it is in fact neither. That is because if you look at this list, like because of the exclusive nature of it, the only way to tell if it's neither is if these two are wrong, because these are the only three possibilities. Either it's parallel, it's perpendicular, or it's neither. So if it's parallel, that means it can't be these two. If it's perpendicular, it means it can't be these two. Which means if it's not these two, it has to be neither. It's a logical statement. So let's talk about how to show something is perpendicular, and let's take a second to do the next step, which is how to use parallel and perpendicular to find another equation. So let's take a look here. Make sure I have those tests ready for when I need them. All right, how to check for parallel, perpendicular, or neither. Well, it kind of depends on what's given. So in all cases, your first step is you must find slopes. Even if they're in the picture, if the question says to verify that they are parallel or perpendicular, you can't just look at them and say, I'm pretty sure. Like I did earlier, but that's because I was viewing it as an observation. If I wanted to verify that it's parallel or perpendicular, or check that it's parallel and perpendicular, which is the same statement, I need to do it mathematically using these two checks. So either way, you need to find M1 and M2. Now, how do you find M1 and M2? Well, you can use the slope formula of y2 minus y1 over x2 minus x1. This works well if you're given points. You can use rise over run. This works well if you're given a picture. And of course, you can also use the delta definition, but the delta definition is all the same as everything else. And so it all ends up being the same. And finally, you can actually use the equation if you're given the equation. Because if you're given the equation should naturally contain the slope, provided that it's one of our 5 basic ones. And don't forget, our 5 basic equations were general form, which, as weird as this sounds, general form is the least used because it's not very useful. You also have things like slope-intercept, which is y equals mx plus b. And you have point slope, which is y minus y1 equals m x minus x1. Notice that in each of these equations, it's easy to figure out what the slope is because they give it to you. It's the coefficient of the x. It's the coefficient of the parentheses. Up here, it's a little harder. You have to put it into one of these forms algebraically, but it can be done. Remember, the goal is you must find the slopes. Okay? Once you find the slopes, step 2 is you have to check individually. You need to check, is it parallel? And if the answer is yes, then you can go ahead and stop. If the answer is no, then you need to go ahead and check perpendicular. If the answer is yes, then you can stop. If the answer is no, that means the answer is really neither. This is a little flow chart. So what you want to do is you want to first check, is it parallel? Yes or no. Why parallel first? Well, because if you look at the thing, it's easiest, right? Are they equal? That's an easy check to make. And so you should probably check that one first. Are they equal, yes or no? If the answer is yes, you stop because the answer is parallel. If the answer is no, then you keep going. If the answer is no, you need to check perpendicular next and ask that same question. Is it perpendicular? Either this statement is true or it's not true. If the answer is yes, we stop. If the answer is no, it's neither. We would stop and say parallel. If the answer is no, we need to stop and say perpendicular. So, let's put this in action. Now to get our hands into the little flow chart, let's look at, I'm going to start by doing points because that's the harder one, and then quickly do lines, and then do the last piece, which is the other one. Okay, so let's verify with points. So we have the points 3, -4, and 5, 2. We're going to quickly find those slopes. We also have the points 4, 6, and the point 4, 1. So I'm going to go ahead and make sure my first step is I need to make sure to determine, are these in fact slopes? We need to find them. So I'm going to take that step for each one of these, and let's do that math. Going quickly here, I would do y2 minus y1 over x2 minus x1, and I end up with, on top 6, on bottom 2, which is 3. On this one, the same process. I do y2 minus y1 over x2 minus x1, which is 5 over 0, which is undefined. Okay, so now let's make our checks. Are these parallel, perpendicular, or neither? Well, let's check parallel first. The answer is no. 3 is not the same as undefined. 3 is a value, undefined is not a value. And so parallel, no. What about perpendicular? Well, I can plug into that formula that I have from before. But the problem is, when I plug into a formula, I can't plug in an undefined value. So again, the answer is no. And so in this case, the answer is neither. It's that straightforward. Let's look at one that should more adequately fit this mold. Okay, I'm going to use one of these points again. So I'm going to use L1 is 3, -4, and I'm going to use 5, 2. Let's make an adjustment to one of these. Let's move one of the points. Instead of having the point 4, 1, I'm going to assume we have a different point. Let's say 2, 1. Well, just like before, we're going to check to see if these points create something that is parallel, perpendicular, or neither. First, slopes. Doing it quickly here, I'd get the same slope for that first one. I'm going to shortcut some of my work there because I didn't change anything. For my second one, I should go ahead and do the math. So I would do y2 minus y1 over x2 minus x1. So y2 minus y1 would be -5 over -2. -5 over taking -2 is actually 5 over 2. And there's my answer. Okay, let's perform our checks. Is this parallel? Well, remember, parallel means they have to have the exact same value. The first slope has to equal the second slope. Is 3 equivalent to 5/2? No. 5/2 is actually 2.5, and so they're not equal. Well, let's check perpendicular. I'm going to multiply them. Is the first slope times the second slope equal to -1? Is 3 times 5 over 2 equal to -1? The answer is no. 3 times 5 over 2 would be 15 over 2, which is 7.5. That's not -1. And so the answer for this one is neither. As you might imagine, the most common answer is neither. That is because, in general, if you take an infinite number of lines and put them all on the same page, most of them are going to be neither. It's very rare to have, things that are parallel with things that are perpendicular. And so get used to getting neither as an answer. But you can't jump straight to neither. You have to check parallel and perpendicular first. I recommend doing it in that order. Parallel first, perpendicular second. And with these two tests. Now, let's get into the meat of the assignment. Your assignment focuses upon a different property of parallel and perpendicular. How do we find a parallel line? Or how do we find a perpendicular line? Well, it turns out it's the same basic way. Step 1, in each case, is we need to find the slope. Step 2 is where things change. If they're parallel, what you do is use the same slope and a point to write an equation. If they're wanting to be perpendicular, you need to, I recommend using the bottom formula. I would recommend plugging -1 over m as the new slope and point to write an equation. So neither one of these worked. So what if I said, hey, find one that is parallel or perpendicular to 3, -4, and 5, 2. Make one work. And let's say I want them to go through the point 4, 6. So this is my original, and this is my new. How do I do that? Well, in both cases, I got to find the slope. Thankfully, I already did that work. But normally we'd have to go through the math of finding it. I know the slope in this case is 3. Now, if I want to find one that's parallel, I need to use that same slope and the point to write an equation. Remember from last time how I said the most common formula in calculus is this one? I wasn't lying. Okay, so what I'm going to do is I need to use the same slope, 3, as well as the point. Now my point in this case is 4, 6, so use the x value. And the y value. And this is an equation that is parallel to these two, but through this point. Now, this exact equation I'd have to actually simplify farther in order to get the answer, but this is the answer to what the parallel line would look like. If I actually do that math, I need to distribute y minus 6 equals 3x minus 12. Add the 6 over, and then y equals 3x minus 6. This line would be parallel to these 2 points, but through this point. And in a second, I can showcase that using Desmos. Okay, you can see right here. Notice that I have my point 5, 2, as I was given in the problem. I have my point 3, negative 4, as I was given in the problem. Notice my purple line is the line 3x minus 6, and these are parallel. And notice what point it goes through. The point E, right there. Oh my gosh, hand, work. Right there. 4, 6. And so it meets our criteria. It goes parallel to 3, 4, negative 4, 5, 2, but it goes through this particular point. Let's compare this now to our other one. So how do we do it if we wanted to be perpendicular? Well, what we do is we take the slope that we know is true, plug it into this version of the formula, and then use that new slope and the point to write an equation. So let's start by finding that new slope. So this would be negative 1 over 3, which is negative 1/3. And so this is going to be my new slope. This is my new slope. This is my perpendicular slope. Okay? So I would do y minus my y1 value, which is 6, equals my new slope, which is negative 1/3, parentheses x minus my x value, which is 4. And this is a line that is perpendicular to these two, but through this point. So let's take a moment and do that step. I'm going to simplify. So I'd end up with y minus 6 equals negative 1/3 x plus 4/3. Add the 6 over, I end up with y equals negative 1/3 x plus 22 over 3. Taking some rapid math there. Well, let's pull up Desmos and see if we get this to be perpendicular, as it should be, right? In theory, this line right here, when graphed, should be perpendicular to these 2 points, but going through this point, which means we've now seen 2 different lines, these are clearly different, that both go through this point, but have very different properties. One property being parallel, one property being perpendicular. Well, let's go ahead and look at Desmos. So now I put in my line, y equals negative 1/3 x plus 22 over 3. Notice this black line over here. This black line is clearly perpendicular. I'm going to hide that one. It's clearly perpendicular to this green line, which is the original line, the one that goes through 3, 4, or sorry, 3, negative 4, and 5, 2, right? It's clearly perpendicular, and yet this black line goes through 4, 6, as expected. And so we've seen now 2 different lines, the purple line and the black line, which both have a property related to these 2 points. But neither one of them has different slopes, right? The purple line has the same slope, making it parallel. The black line has a perpendicular slope, making it perpendicular. And so this is your homework tonight, is to be the ability to take given points and find lines that are either perpendicular or parallel to them. That'll be it for this weekend. Don't forget, we have our first official Zoom session starting at noon, but the teachers' meeting takes place right before that, so do note that that may be a reason if I am a minute or so late, is because the teacher meeting ran over, but I should be there. I'll be posting the Zoom link starting at noon, and any person that wishes may come in and ask any questions they wish about any of the problems. I look forward to seeing you guys there, even if it's just a chat, in case you don't have any questions. If you do, make sure you get those answered, and I'll see you guys then. If not, have a good weekend. And all homework is due tomorrow at noon. Have a good rest weekend. Bye.